Welcome to this tutorial about designing contact experiments like indentation measurements or scratch tests for coated or treated surfaces by the means of the software TestOptimizer. First, the question may arise, why shall I design my contact experiments? Because there are several standards or norms which define specific procedures for testing, for instance, the hardness on materials or the adhesion of coatings. The problem is, though, that many of those standards or norms are either not designed for coatings at all or are not well suited to coatings. And I would like to show or demonstrate this on a few examples. For instance, the Rockwell hardness test HRC, which has been performed on a 20 micrometer thick titanium nitride coating, would result in the main stress field located deep down in the substrate, resulting in the sensitivity of the measurement being also deep down in the substrate. Exactly 99.3% of the measurement information is coming from the substrate. And this means in turn that only 0.7% of the measurement information is coming from the coating. So, and this ratio gets even worse on thinner coatings or more complex coating structures like multi-layer coatings. So it could well be that you end up with measurement information from the coating which is below the level of your noise floor. Another example I would like to show you is a scratch test which has been performed according to the standard 1071 on the exactly same coating. You may again see easily that the main stress field is located deep down in the substrate, as is the maximum of the stress field, which leads to a severe damage of the substrate. And solely due to this damage of the substrate, the coating eventually fails. So in the end, you gain no knowledge at all about the coating you have been interested in or the adhesion of the coating on the substrate. I hope it is clear now why it is important to design contact experiments for coated or treated surfaces. And now I'm going to show you how you can design contact experiments specifically for the coatings you are interested in a quick and easy manner by the means of the software TestOptimizer. These are just a few hints popping up here which are not relevant to our tutorial. Please note that this is the light edition of TestOptimizer, which has only limited features. For instance, it supports only single layer coatings. If you are interested in more features like coatings with up to 100 layers or an adjustable friction coefficient or stability limits for the indenter tip, then do not hesitate to contact us, as there are other editions of TestOptimizer in development right now. And this is the home page of the software TestOptimizer, and it is subdivided into 3 sections according to the 3 steps you have to take to design your contact experiments for coatings. The first section at the top is the material definition section. The second section below allows you to specify the aim of the investigation, and on the right hand side is the last section which allows you to select the types of experiments you want to perform. So let's begin with the first step, the definition of the mechanical properties of each constituent of your sample. So you may either enter the mechanical properties as far as you know them, but usually you still want to measure them, at least of the coding, so you may not know them exactly. Therefore you can already also guess them, of course, or obtain reference values from the literature, or you may choose materials from the provided database. What I'm going to do now. I select a conventional titanium nitride coding for titanium nitride for the coding, and a very conventional steel for the substrate. So you may have noticed that only the elastic mechanical properties have been set accordingly, because the database can't know the thickness of your coding. Therefore, we have to enter it ourselves. I don't want to use a 20 micrometer thickness again, because it won't be very difficult to dimension contact experiment for such a big coding. Therefore, I'm entering 2 micrometers as thickness, and the last part of this first step is to enter the plastic mechanical properties of the coating and the substrate, which can be done by either entering the hardness and the constraint factor, or by entering directly the yield strength, which has been automatically calculated according to the equation H equals Y multiplied by the constraint factor. In this case, yield strength of about 20 gigapascal, it is still reasonable for the coding, whereas the hardness of the for the substrate isn't, of course. A hardness of around 6 gigapascal is more reasonable, and a constraint factor around 3, about 3 is okay. So we can move on, or we can proceed with the second step and define the aim of our investigation. And there is a list of aims we can choose from. For instance, we can select that we want to investigate the adhesion of the coating on the substrate, and the point of interest is located accordingly at the interface. But in our case, we want to investigate the coating itself. Therefore, we select coating investigation. The point of interest is located in the center of the coating, so we can go on with the last step and selecting the types of experiments we want to have dimensioned. And in our case, for this tutorial, I only want to have a scratch test and an indentation measurement with a Berkowitz indenter to be dimensioned. So finally I can start the dimensioning process. The calculation has been finished now, and it took about 1 minute, which I have cut it out for the purpose of keeping this tutorial short and crisp. However, before we come to the results, the software is showing us a hint with respect to the point of interest. It has been adjusted in order to prevent plastic deformation in the underlying substrate, and thus preventing the sensitivity of the measurement from moving even also down into the substrate. And there is an additional hint about the number of measurements which should be performed, particularly on rough surfaces. Eventually, the software shows us the results for each experiment on a separate page, and you can use these buttons at the bottom to navigate from one page to the other. And each page is subdivided into 3 sections. At the top are the theoretically optimum key parameters of each experiment. Below is the expected stress profile. And at the bottom are a few hints about a physical analysis of such experiments. As I've already mentioned, these are theoretically optimum key parameters, meaning if you don't have, for instance, a spherical stylus with an exact radius of 3.7 micrometer at hand, then of course you have to choose the next best one. Preferably, if it comes to the indenter or the stylus, it should be a bit smaller. So if you have, for instance, in a spherical indenter with a radius of 3 micrometer at hand and one with a radius of 4 micrometers at hand, then you should choose the one with 3 micrometers radius. Same holds for the force range. If your instrument is not able to apply such a low normal load, but only starts at 10 millinewton normal load, then of course you have to start with 10 millinewton. If the difference is not too big, the effect on the resulting stress distribution won't be too significant. I hope this figure shows clearly that this scratch test is perfectly designed for this coating, as the complete stress field caused by the scratch test is located in the coating. By the way, the interface is marked by this white dashed line at the bottom. And the same holds for the indentation measurement with the Bergowitz tip, as the complete stress field is perfectly located in the coating. It is a well-dimensioned indentation measurement, perfectly suited to investigate this coating. So, thank you very much for your attention. This was our brief tutorial about designing contact experiments for coated or treated surfaces by the means of the software TestOptimizer. And do not hesitate to ask us any further questions.